So for the second talk in this session, it's a great pleasure to introduce Rosalba Garcia-Millan from King's College. Rosalba first studied in Barcelona before doing a maths in Barcelona before going to Oxford to do a master's. And then her PhD she did at Imperial, and then started a postdoc at Cambridge with Michael Cates, the Lucasian professor. And she was then awarded an independent research fellowship in physics and astrophysics at St John's in Cambridge. And now she is at, as we said, at King's College. So it's a pleasure to introduce you to speak about field theories of active matter. Thank you.
Thank you so much for the super nice invitation. It's really honor. It's a great honor to talk here for the LMS and the anniversary of Lord Kelvin. So I'm really happy to be here. So I will talk about my work on active matter, and this has different branches. On the one hand, there's the mathematical framework that we are developing to work with these active systems. On the other hand, there's all the thermodynamic aspects of it, and my work touches a bit on all of this, and that's what I'm going to be talking about today. So first, I will introduce active motility, then I will talk about the non-equilibrium behavior of active matter, and I will focus on entropy production as a measure of time irreversibility, and then I will move on to the microscopic theories that I use to study active matter, and I'll give you a glimpse of how this framework works, and how, for example, we use it to talk about emergent behavior in active matter. There was this example of motility-induced phase separation, so I'll talk a bit about that. And so how do we use these field theories to describe phenomena like that, phase separation? And I'll end with some conclusions. So active motility or active matter is out of equilibrium. It's typically made of many parts, many constituents, and each of these parts is in exchanging energy with its environment, let's say, constantly. So fuel is transformed into mechanical work, or that's the typical picture that we have of active matter. And one can think of swimming bacteria. So these are, they eat food from their environment, and they, thanks to some organs like flagella, they propel themselves in their medium. There are many examples of active matter. Not all of them involve self-propulsion, but this is a very large class, and that's what people have in mind when we talk about active matter. So this is the very classic picture of active motility. This is a bunch of cells. They are E. coli, and they have this flagellum. They swim, and so they use this flagella to swim in a straight direction, and also to, at certain sudden times, to reorient themselves. So this is a type of motion that we have modeled. The field has modeled, and it has called run and tumble motion. So so very large class of active matter has to do with living systems, but there are also synthetic systems, or like this experiment. So this is similar to what Luke was showing earlier. There are some microspheres. They have a coating on half of this sphere, so here this coating reacts chemically with the environment so that it forms a bubble, and this bubble or this gas that is being formed as a result of this chemical reaction is propelling the particle in the environment. So this one is not activated through light, but it's just a chemical reaction that is happening as long as there's a chemical reactor left. So what you can see is that these particles follow this persistent motion. So they swim in some sort of straight line, but they also reorient themselves, and this reorientation is happening constantly in time. So this is the main difference between this model, which we call active Brownian particles, and the previous mode of motility, which is that here the reorientation is happening continuously. So when we want to model this type of motility, often we start with writing down this equation. This is an overdamped Langevin equation, and it's telling us the velocity of a particle that is at position x. So this velocity typically has these three components. And the first term is the self-propulsion. So this is a correlated noise. And this is, it has a correlation time. And over this time, the particle has a memory of its orientation. So over this time, the particle moves in a correlated direction, and that's what makes it self-propelled or self-propulsion. There's a second term, which are the external forces. So this may be due to interaction with other particles or interaction with the environment, an external potential, and so on. And there's also a thermal noise, and that's just a Brownian type of noise. Okay, so if I compare the two types of motions that I talked about, run and tumble and active Brownian motion, both of them have the same type of Langevin equation. What differs is how we model this orientation. In one case, the evolution of this orientation is taken from a uniform distribution every time that the particle reorients. In the case of the active Brownian particle, this orientation is diffusing in the space of orientations. So now let me move on to the non-equilibrium behavior of active matter. So as I said, active matter is out of equilibrium, and we want to understand how this is manifested, and we want to be able to quantify it, even to exploit it, to do some control with it. So that's why we need to understand it. So, and because we are talking, celebrating Lord Kelvin, let me talk about the laws of thermodynamics. So we already have seen this, but in the first law, one important consequence of the first law is energy conservation. And so it's telling us the change on the internal energy of a body is the sum of these two terms. One is the heat, and the other one is the work. And whether it's a plus or a minus sign, it depends on the convention that we use. But essentially, these two exchanges of energy contribute to this change of internal energy. So one very important and fundamental consequence of this is that work is the mechanical equivalent of heat. And so often we talk about work or heat interchangeably, and we don't even think about the difference between them. So fundamentally, they are the same. And the second law of thermodynamics, as was mentioned before, gives an arrow of time. So it tells us processes in nature are irreversible. If we place a hot body next to a cold body, there's going to be a flow of energy. And it doesn't mean we cannot go back to the initial state, but if we do so, there's going to be an energetic cost. So there's some loss of energy that we do every time that we try to revert this process. This loss of energy is absorbed by the environment, so it's not lost on the whole. But it is lost if we think of the work that we have to do in order for that process to take place. So it also gives us this expression for the entropy. So there's a function, there's the entropy, and that tells us, well, how this exchange of, or quantifies how this exchange of heat takes place. And because there's irreversibility, this is saying, well, any such process is going to produce a positive amount of entropy, unless it is reversible, at which case, the system is at equilibrium, and so the entropy. So this law brings together these concepts. Non-equilibrium or a process out of equilibrium produces entropy, and we are able to observe it because the process is irreversible. So let me give you an example. So this is a very beautiful experiment and very well known in the community of active matter. And this is a ratchet wheel immersed in an active bath. So this bath is simply a pool of water with many swimming bacteria. And because these bacteria move persistently, they are able to turn this wheel around. What happens is that because of this asymmetry, the bacteria simply get stuck on one side, tend to get stuck on one side rather than the other one. And that's why the wheel turns around. But it really illustrates this idea of, well, irreversibility. So if we imagine the movie running backwards, we can tell that's really not what we expect to see. So this is what we expect to see. This is an irreversible process. And so, well, there is work. So we could, in principle, attach some mechanics and extract the work from this. And therefore, well, this is showing how active matter is out of equilibrium. And we want to be able to do something like this. So from the second law, we can write down an expression for the rate of entropy production. So here, so on the left-hand side is what we want to calculate. On the right-hand side is what we have or can infer from particle trajectories. So this is saying on the right-hand side, we have an average rate of dissipated heat. And so we can measure that, we have the temperature, and so that's all good. If we have like a stochastic trajectory, Sekimoto came up with this expression. So here you can, well, I showed earlier the Langevin equation. So this term here is giving us a force. This is a displacement. So force times displacement is a work. So here you can see the equivalence between heat, work of that. So this is a way to calculate this entropy production by using that expression. Another way is this one, where we know the probability that the system is in a microstate, and we also know the rate with which that system changes into any other state. So these two very different frameworks for the entropy production are equivalent for Markov processes. So, okay, well, we want to do something like that for complicated systems. So I'll show an example in a second. First, just let me show the simple case. So, well, Thomson was concerned with the heat equation. So this is another take on the heat equation, the solution. Here, the example is we have a particle that diffuses with a certain diffusion constant and has a drift. So, yeah, in this case, the drift is constant. What is the entropy production of that particle? And we know the equation. It's the heat equation with a drift. We know the solution is a Gaussian distribution. So we have got all the information we need. We can calculate the entropy production in closed form. And this is the result we obtain. So why I'm showing this is because essentially all the complicated examples are going to be compared to this base case. So there are two terms. Here, the first term is from the relaxation. So initially, the particle is placed at some point. As in time evolves, this particle is going to diffuse and reach some sort of steady state. So that's the entropy produced in that process, the relaxation, is given by this term. And then it's this other term, which is the entropy produced by the drift and the diffusion. And it's a very simple expression, but it really is like the benchmark that we compare to. So I was saying we want to calculate the entropy production of much more complicated systems. And here I show, well, let me talk about motility-induced phase separation. So this is a movie where we have many active Brownian particles in a confined space, and they interact with each other repulsively. And as they do, they form some kind of clouds. And at some point, one of them nucleates, and then this creates some cluster that grows and keeps growing. And at some point, the system has separated into two phases. So one is the gas phase, where particles move essentially freely. And then there's a liquid phase, where particles are really subject to very strong interactions. And well, so here the system has separated. And this is happening for two reasons. One is because of the persistent motion, so that's why it's motility induced. And the other reason is because of the repulsive interactions. So these particles do not directly attract each other, but because of their microscopic dynamics, it looks as if they do. So in the end, they end up spending a lot of time together. And if we were to describe this system, we would think, well, these particles, it seems like they attract each other, and so they like to spend time together. So I will call this effective attraction. It's not a direct attraction, but effectively it is. Okay. So I found this quote by Lord Kelvin. I was a bit surprised, so maybe there's more context to it. I'm not entirely sure about it. But he said that apparently that there is nothing new to be discovered in physics, and all that remains is more and more precise measurement. And so, well, I think for the second part, knowing the microscopic details, very precisely, is not enough. It doesn't allow us to explain the full picture. So how do these emergent behaviors come about from this microscopic dynamics is something that requires much more, and is, to this day, is an open challenge. So here comes field theory. So this is mathematical framework that is built to be able to deal with many interacting degrees of freedom. So first, we need to know where we are. So if we have a scale from micro to macro, and where in the microscopic scale we have the flagella, we know all the details of those self-propulsion. And in the mesoscopic scale, we have the trajectories. And in the macroscopic scale, we can see this phase separation. The field theory that I'm going to talk about sits here. And what we want to do is to be able to explain the macroscopic picture from the intermediate mesoscopic dynamics. In fact, I will refer to this one as the microscopic dynamics. But there's always, you can always zoom. So that's a typical criticism, but of course you can always zoom in and go to the final picture. So to talk about effective attraction, this is a project that I've done in collaboration with others. We look first at a much simpler process. So here we break down the problem to the simplest case, which is two run-ensemble particles on a ring. And so these two run-ensemble particles, because it's in one dimension, they either swim to the right or to the left. And with a certain rate, they tumble, which means they change their direction of motion. So if I run a movie of this process, they move freely, and whenever they meet, they interact. And this interaction, in this case, it's a soft repulsive interaction, which means that they get stuck, but they could cross. So when they meet, they get stuck, and the only way they can separate again is either because one of them tumbled and so they separate, or because by some fluctuation they crossed. Okay, so as you can see, when they meet, they get stuck, and they do spend some significant amount of time close to each other. So that's what we call effective attraction. They do not attract directly, but effectively it looks as if they do. And I'm going to talk you through the mathematical details of the calculation, I mean, without going too much depth. But so here, as I mentioned earlier, we start with the Langevin equation, and these are the dynamics of both particles. There's one at x and one at y. They have a fixed self-propulsion speed that changes sign with a certain rate. There is an interaction force that is given by a potential, and there is a Gaussian white noise. And the choice that we make for this potential is really important, because in this problem, we want to calculate everything exactly or in closed form. So not every potential is going to work. We choose a Yukawa potential. And if we take the limit of the very large system size, this Yukawa potential on the ring can be approximated as this exponentially decaying function. So that's just a picture of this potential. Now, when we write down field theory, what we want to do, the first thing we want to do is to write down an action. And in this case, because there are two types of particles, they can be right moving or left moving. There are two types of fields. And so if you look at A0 gives us the bare dynamics. You can see that the drift has opposite sign. So that's because one is right moving, the other one is left moving. And on top of that, there's this tumbling, which is here. So this gives us the bare dynamics of the system. Now, on top of that, we have the interactions, and these are much more complicated terms. So in fact, there are many interaction terms. They account for every combination of a right-moving particle interacts with a left-moving particle and so on. And they all need to be taken into account. So in field theory, we often use diagrams. And these are the bare propagators. These diagrams help us they are a bookkeeping device. So it's a method so that we don't lose track of terms. And so these are the bare propagators. They just talk about propagation, or a particle is created and we can measure its presence at a later point in time somewhere else. And then there are the interaction vertices, which tell us about what is the effect on the velocity of a particle due to the presence of another particle somewhere else. So this is what these interaction couplings contain. And so, this is a microscopic theory, and it's an exact representation of the microscopic dynamics. Now, this is, I think the mathematical details get as far as here. So from here, what happens is, remember, we want to characterize effective attraction, and the way to do that is by looking at fair correlations, or let's say 2-point correlation functions. So it turns out in this system, what we need to do is to find a smart way to account for the following feedback mechanism. The two particles move, and as they move, they also interact, and their interaction feeds into their motion, and their motion feeds into the interaction, and so on. I mean, we can go on forever. So that there is a way to calculate that effect, let's say in a recursive relation, and that's how, in a perturbation expansion, we can calculate these correlation functions. So these are what we call these effective interaction vertices or effective potential vertices, and they account for all these feedback mechanisms between motion, interaction, and so on. Now, let me go to the results. So here I'm showing the 2-point correlation function of these two random tumble particles as a function of the distance between them. And the color bar is the interaction strength. So this is our perturbation parameter. For no interaction, which is the blue color, this distribution is uniform. So the two particles don't see each other. So their distribution, the length between them is uniformly distributed. And as we turn on the interaction, we see two things. One is that at 0 distance, there's this dip. And then away from 0, there's like a little bump. Okay, so the dip at 0 distance shows repulsion. The bump shows some attraction or suggests. Similarly, now this is a similar plot, but instead of tuning the interaction, I'm driving the system away from equilibrium. So when the system is at equilibrium, this distribution is just a Boltzmann distribution. So that's the black line here. And as we drive this system away from equilibrium, meaning we turn on this self-propulsion, then the particles start to spend some time close to each other. Okay, we can also, as a, let's say, side product, we can also calculate the correlation functions for the partial, like taking into account the internal state of these particles. If they move against each other, so that's the purple line. If they move against each other, they are jammed at a certain finite distance. So that's what this peak is telling, what it's telling us about. And if they move in the same direction, whether it's to the right or to the left, they have this correlation function. So as you can see, they repel each other, but there's some other mechanism that effectively keeps them not too far from each other. So this other mechanism is the tumbling. So it's a Poissonian noise. As the two particles separate, they still tumble. And so that's what we can see how one distribution leaks into the other one. Okay, so here we wanted to describe this effective attraction, and to do that, this measuring idea, it's important to find an appropriate observable. So maybe measure in this case is to find this observable. And this is just the compressibility factor. If you have worked with a structure factor, that's the lowest mode or the limit as k goes to 0 of the structure factor. So here we are plotting this structure factor as a function of our perturbation parameter. And the reason why I'm showing this is because I want to point at two things. So one is, as we increase this perturbation, this interaction parameter, the leading order behavior is effective repulsion. So there's some threshold below which we say, okay, the system is behaving repulsively, above which we say it's behaving attractively. So initially, the system goes into repulsion, which is what we would expect if we just have repulsion. And at some point, we have some higher nonlinear terms that kick in and make the system turn from repulsion into attraction. So that was really what we wanted to characterize. And of course, now that we've got this, we can say, well, we can find this crossing point for a set of parameters. And that's how we draw this phase diagram. So in different places of the parameter space, we can say, well, the system is in the effective repulsion regime or in the effective attraction regime. And well, we can play with this a bit and have different interaction distances. And we can see, for example, that this profile changes with parameters. So it's not always, for example, if we compare the purple or the pink line to the, let's say this green one over here, these are really different functions, and it's not, we could not massage one into the other one. Okay, but I was talking about entropy production earlier. So, well, okay, so with this method, we can also find the expression for the entropy production. What is really important here is that we solved for P plus plus and P minus plus. So we can simply plug this into the expression and see what this entropy production looks like. So here, the entropy production is drawn as a function of this interaction strength. So for no interaction, we have the value, the initial value that I showed earlier, this W squared divided by the diffusion. And as we increase the interaction, what happens is that particles slow down. And so that's the explanation why the entropy production decays. And this happens for different parameters, and we can see, well, that makes sense. As the particles get jammed, the system is not diffusing, or it's not dissipating so much heat. And going back again to the many-body system, okay, well, we don't have the full correlation function. I mean, that's a really hard observable to calculate. And in a system like this, I would say, I mean, nearly impossible if someone doesn't come with like a really smart idea. So, so what we were interested in is, well, let's see how these particles, what's the entropy production per particle? What does it look like when we have a system that is phase separated? So first of all, here on the gas region, these particles that are moving essentially freely, they are in the one, so one is normal, it's normalized, but they show the free motion entropy production. And inside the blob, it's quite interesting to see first that there are these, that the majority are blue, so it's in the negative region. They are, we could think of them as frozen, so they don't dissipate so much. And there are some really bright, super entropic, I don't know, super duper particles. So that's something that we are still, well, we want to understand why are there these super bright particles in this picture. And yeah, what's the explanation for this? Also for the structures inside of this blob. Anyway, this brings me to the end. So one of the conclusions is that I talked about Doepeliti field theory. So this is a framework that retains the microscopic dynamics of the system, and that we want to use, or we are using to study active matter. So this is a new tool. And what makes it important is that it retains these particle correlations in an exact way. And so we can use this to calculate observables perturbatively. So that's an advancement compared to other frameworks where often people do approximations, and sometimes it's not really well understood how these approximations are done. So this field theory links the microscopic dynamics with emergent phenomena. And here I showed the cases of tumbling, drift, and also pairwise interaction. But there are other types of interactions or reactions that we can include. We can have birth and death, coagulation, and others. So we use this in these examples to characterize effective attraction and to calculate the entropy production rate. But of course, there are still many challenges. And one of them is to move on to the many-body system and other types of interactions. So for example, here I mentioned the hardcore interactions. This framework presents some challenges. So for example, some divergent some divergent loops, for example, when we calculate. And so, yeah, so these are some of the problems that I'm working on together with my collaborators. So I would like to thank all of them and also all the institutions that have supported me, and also all of you for your attention.
Thank you very much, Rosalba, for a really informative talk, and I'm sure there are plenty of questions. Great, Andy.
Yeah, your sort of super diffusive particles are really bright ones. Could they correspond to defects moving through the frozen bit? So it's not really one particle that's got this super diffusivity, it's a chain of them handing over to each other to resolve a defect.
Yeah, so I looked into this a bit, and it is related to that. So I think there's something there also, because so these defects move, you can see them forming and evolving, but they are also quite persistent. It takes some time for the blob to rearrange itself, and when you look at this in the movie, you also observe that these yellow particles stay yellow for a while. So I think it has to do with that, but of course, to make a statement about it, you need to look very carefully at all the forces that act on a particle and why, so that's still an open question.
Yeah, in the original movie, it almost seemed like there were little rats just throwing crystalline bits, but a sort of bit of a mess around. Rearranging. The other thing I wondered about is there any non-trivial scaling behavior you've observed that you could like renormalize it, get a renormalization explanation?
Yeah.
It's right, the obvious trick.
So this problem looks very simple. Like there's only two particles, they have this very well-defined interaction, but we looked very hard and there was no like any sort of back of the envelope calculation about, oh, this length surely must be really characteristic and there must be these two length scales competing. There was nothing really sharp or nothing really like, oh yes, definitely this length scale must be it. So yeah, we looked into it and it was not so obvious. Yeah.
Yeah, thanks, Rosalba. So preaching to the choir of that. So actually following on from the question, and then another separate question. If you average the entropy production in the cluster, what do you get compared to the bulk?
Wait.
So there's
The cluster compared to the bulk?
Yeah, so if I average, so average over the blues and yellows and some of the oranges in the cluster.
It's in the blob, yeah.
Yeah, in the blob, and compare it to the bulk. Is it just below, just above, or is it?
But the bulk?
I mean, like the vapor phase of the. So basically, outside the cluster.
It's below. So this blob really brings it down. Okay, here you need to. So we are thinking of the entropy production per particle. Yeah. So it grows with. I mean, you have to compare it to the number of particles as well.
Okay,
but anyway,
yes,
if you,
in the bulk.
yes, you can easily. But anyway, yes. So when you compare the system where all the particles are running freely, that compared to the system where there's a cluster, the entropy is lower where there's a cluster.
And a separate question just on this effective attraction. So it's I guess a question in the vein of Ms. Thompson. So if I was to take a particle on the edge of a cluster and to literally pick it up, what's the work done required? So basically, how effective is this attraction? Do you see what I mean? Because you'd think that there's no literally stickiness, only persistence, but how much work on average do I need to do to take a particle and pick it up?
I don't know. Yeah.
So it could be interesting even in the two-body case, when they're bumping heads, an external guy was to pick one up. Is on average, do I spend work?
I think yeah, I think so, but no, good question. Okay, thanks. No,
Yeah, so fabulous talk, and maybe just to follow up again, on what's been said before. That simulation did show what looked like a polycrystalline structure. Could you bring it up, the movie, which was the aggregation to the final clump?
here.
Yeah, so while it's running, so there is this coarsening that's happening too. So while that's running, getting to its final state, are there scaling laws associated with the rate at which the average length scale of these growing clusters appear? Just want to take the scaling behavior.
Yeah, so by the way, then now I go back to, sorry. The thing is, if people who have described this phenomenon from the macroscopic point of view, maybe they have come with some scale. So I was keeping in mind the microscopic point of view that I had been talking about in the two-particle system. So I think that there's some comparison.
In some sense, it's like maybe linked to someone like John's interest. This looks like a polycrystal.
Yeah.
In the sense of you have well-defined crystallographic orientation. We have grain boundaries, but those are clearly mobile.
Yes.
So in that sense, that looks to me where the concentrated entry production is occurring along those mobile grain boundaries. And that relates to the question here now about basically effective surface energies, the work done. And so to sort of resonate off of just one last thing, Mike Case, who spoke on Wednesday at the other Kelvin event on these active matter systems, he was focused a lot on entry production that was localized on interfaces. So in that sense, to what extent you take the data, are you seeing essentially interfacial entry production? All the physics is interfacial.
So Mike's work on this entropy at the interfaces is done differently. So it's a different way of calculating the entropy production. So it's a different, I think it follows from this. I showed the two definitions for the entropy production, but there's another one, which is the log ratio of path probabilities. So his work is based on that, and he uses that to assign an entropy to each particle. That's different to what I was showing, where you can calculate the entropy produced per particle from the microscopic dynamics and evaluate that at each point. So the two both should maybe be consistent with each other, but well, they in some ways they are different assumptions, and so that's why it might be not exactly the same. So in our case, we do see entropy at the interface, but what is really surprising is to have these very bright spots where, there's, because of the topological defects or some other reason, they really contribute quite strongly. But most of the bulk within that cluster is essentially frozen. So yeah, it's I would say it's not super straightforward to say, oh, it's interface versus bulk, and that's it. It's a bit more, I think, convoluted. Thank you.
Could you say a bit more about this field theory? I didn't understand it at all. You seem to suggest that it was rigorous. I mean, it contained all the information from the original problem, but I don't understand what the fields were, or having got from the original problem to the field.
Yes. So first, okay. In most field theories, we work with densities. And this field theory is different because neither of these fields is a density. These come from quantum mechanics. So there's a process of second quantization, and they are ladder. So they come from ladder operators. They represent creation and annihilation fields. So, but however, this field theory is not relativistic. It's not quantum anymore, but it uses these tools from quantum physics to describe a system where the degrees of freedom are discrete. So maybe the important difference compared to these other field theories that use densities as fields is that these degrees of freedom are here are discrete versus when they are continuous, when we use density. So
What do the fields represent?
yes,
What is-
so there's no
I guess with
Fi-
phi and psi, they pointed to different aspects of the particles.
So first, there are two types of fields. One is the creation field, and the other one is the annihilation field. When we write down the path integral, they are already complex conjugates of each other, and we can.
What's being created and what's
So,
being?
is
There's only two
sorry.
particles, right? And there's always two particles.
But isn't it when they bump heads, isn't that some kind of annihilation, and then when they leave?
No.
No.
So what is being created and annihilated are particles. So this tells you, okay. Initially, when you want to calculate an observable, you have to initialize the system and you say, this system is initialized with two particles. And in your observable, you have to put down two creator fields to create those two particles. And then the action carries the dynamics, and you want to then measure, for example, when you calculate the 2-point density, so you have to probe the system for two particles. So then you put down two annihilator fields. So there is a back of a story here. So there's first the dynamics. Initially, this was used to describe chemical reactions. So it's very easy to account for particles that are created and destroyed. And so you use ladder operators to describe those processes. And then the field theory, I mean, these ladder operators are transformed into fields, and then you can use that in a path integral. So that's the formalism behind this. In the end, when you don't seem convinced, but in the end, you can, let's say the recipe is that you write down a Fokker-Planck equation, and directly from there, you can write down the action, and then you can use that to calculate observables.
Okay, I think maybe you could continue this in the break, because I think we're kind of on the button for time now.
Yeah.
So can we thank Rosalba